Hello.
Hi, how are you?
Hi, Sarah. Hi, Mohammed.
Hello. Hi, Negar. Good to
Hi.
see you.
Thanks for texting. I wasn't sure that if you're gonna meet.
No, I knew that you are gonna be on time, but I thought it never hurts, you know.
Yeah, that's good. Yeah, and I can share my screen. You see that everything is working.
Exactly.
I'll share. Yeah, that's nice. Thanks for the invitation,
That was
Sarah.
exciting. I love all the sculptures in the background. Are those
Thank
your
you.
work?
Yes, and you're gonna hear about them, I think, in the presentation. So.
Okay, cool. Yeah, they're really
Thank
beautiful.
you
I just
for
love the
being.
white on white.
Thank you for being so generous with your time. I know it's your sabbatical, so that means a lot to us.
Sure, thank you. Yes, I'm gonna have a few, and I arrange all of them this week. So I started with you, and then Texas A&M, then Illinois University.
Oh,
So
I see. Okay.
So it's nice to be connected to bigger, audience than just
Sure.
your own things. Yeah. Okay, so I can share my screen for a second so you can check. Oh, I think you see my notes, correct?
Yep.
Okay, so wrong sharing. Okay. I think this is it.
And I think we are live on YouTube, right, Sarah?
Yes, we are.
Okay, sure.
Okay, this is.
I don't know if you can.
I'll behave, so I promise.
So you see the screen, correct?
Yeah, that looks great.
Can switch back to my presentation. So do you want to stop sharing and after the introduction I start sharing? I don't know. How do you want to do that?
Yeah, and then you're not giving a tease to everyone.
Okay, so I'll stop now and then we can do that. Okay, good, great. How is things in East Coast? Is it going? Is it cold? Is it?
No, it's actually really warm today. It's like 60 and rainy. It's so weird. And then it's just been the weirdest February. It's been like 20 degrees and then it'll go up to 60.
I know, it keeps changing.
I know.
It's crazy. By the way, Negar, I just want to tell you that in case there aren't many attendees, don't get disappointed because many people will watch it through our YouTube channel. So the timing, I mean, there is no perfect timing in our in our school because some of the time slots work for some programs, some of them they don't work for other programs. So this one, I know that there are students who have classes, but we can't do anything.
Yeah, no worries. Yeah. I would be happy to present for this group even.
I know. I always say, I think
that you never see my research presentation, so it's going to be nice even, you yourself know what I'm doing.
I always say you need the right audience rather than just
the number. Yeah. And I posted on Instagram. I know that, the time doesn't work in a lot of countries, but I thought that maybe somebody else want to join. It's
exactly.
Nice open.
You probably will. It's funny. I think people think they can't get in until 4 o'clock. And so they kind of wait. And then at 4, it's like the gates open. It's kind of funny. So.
Yeah.
I know that I'm supposed to be professional, but please send my regards to Ali Reza.
Okay, sure. Yeah, I will.
So how are you doing, Sarah? Your classes are going well?
They are going well. Yeah. It's just, with accreditation coming up, it's just been like a nonstop semester.
I know.
So once the beginning of April comes and goes, it'll be a big breath of relief. And then I'm going to the SELA conference in New Mexico in March, which will be just like another hurdle, but it's good. It keeps me out of trouble.
Is it in Albuquerque or?
No, it's in Santa Ana, Pueblo, which is just north of Albuquerque and south of Santa Fe. So I'm thrilled because my presentation is at 11 o'clock on Thursday morning. So I'm going to go to Santa Fe on Friday. I'm so excited. I love that town.
That's great. Wonderful.
Yeah. It's so beautiful out there. And I think in March it should be pretty nice. So yeah, it's just, we have a good group of students. I have a really interesting studio this spring with a Quaker group on the Eastern Shore. It's the Third Haven Friends meeting, and they contacted us last fall to see if we would be interested in doing a master plan for their property. It's 7 acres right on the Choptank. So students have really responded to that, and the work's been beautiful. So it's been kind of fun, totally different, very historic property and on the water. And so it's a nice combination of kind of history and hydrology and geography. And so it's fun. And, a lot of our students are so urban focused to get them out of the city to the Eastern Shore to learn more about kind of that history has been interesting. So.
And Eastern Shore is just amazing. We had a project in Chestertown, a few years ago. Great experience.
It is, and it's so close, and you feel like you're so far away. I don't get over there enough. Mainly because I can't stand the bridge. I get so driving over that. Just oh my God, the Bay Bridge terrifies me. So yeah, I always have to like white knuckle it, and then once I get to the other side, I'm fine. So. It's a little after 4. I don't want to start yet because we need to get people to come. Surprised Dan isn't here at least.
Yeah, I know. I know that there are some classes that start at 4. So some of our students will be watching the video later.
Yeah, but still. All right, look, Negar, if we can wait just a couple more minutes, I don't want to.
Sure, that's fine with me. Yeah.
We are on YouTube, so I want to ask questions if you are enjoying your sabbatical, but I'm hesitant because all this information is going to be recorded officially.
Maybe we should have waited till,
I know.
Started the broadcasting, but
yes.
It's going well, it's
Good.
not. And I'm going to talk a little about, some of the projects that
you are currently working on.
Yeah.
Great.
Yeah. So this is the second lecture in your lecture series?
It's the second one, yes.
Okay.
Well, why don't you get started? Because I don't want to.
I think we will start, and we'll have the link later, right?
Yep.
So I'll just share the link with our students.
Okay.
Yeah.
Okay, well, Mohammed, why don't you introduce our second lecture of the Spring 2020 lecture series?
Absolutely. It's my pleasure to introduce our speaker today, Dr. Negar Kalantar. Dr. Kalantar is an associate professor. Dr. Kalantar is an associate professor of architecture and a co-director of the Digital Craft Lab at California College of the Arts in San Francisco. Her research and practice lie at the intersection of architecture, science, and engineering by bringing together digital and analog fabrication workflows across scales. Her interdisciplinary research practice broadly investigates the potency of transformable design principles, helping to create adaptive designs, building components, and interior spaces that are adaptable and demonstrate real-time morphological changes into users and the environment. Dr. Kalantar is the recipient of several awards and grants from NSF, Autodesk, and Texas A&M, just to name a few. Before joining CCA, she was an assistant professor of architecture at Texas A&M University. She headed up the Advanced Infrastructure, Materials, and Manufacturing Lab at the Center for Infrastructure Renewal. She has organized national and international workshops on additive manufacturing, robotic, and material advancement in manufacturing and architecture. In addition, She has collaborated with several firms in Dubai, Chicago, and New York, including SOM and Gensler.
Thank you. Thank you so much for having me, and thanks for the kind introduction. If you let me, I'm going to share my screen and start from there. Okay. So thanks for having me again. And the topic of today's presentation is design for circularity, backward design for forward progress. So I already, been introduced by Mohammed. Thank you for the introduction. But I want to give you a little feedback, background about what I do and my research interests. I've been, working on research. My research scopes are in different topics of robotic, material system, adaptive design, performative 3D printing, green tech, and plugin in development for fabrication. For the last 2 decades, I've been more involved in addressing research questions through design. And I believe that the design research, we can revisit a lot of problems happening in the built environment by redesigning them and rethinking about them through the design. So I've been working on the wide range of projects, from nationally funded ones to the Silicon Valley startup. And I'm always fascinated by advancement in technology and digital world, and see them as a means to address issues in the built environment. But today I would like to talk about the topic of design for circularity, and first introduction about what is circularity in the design, and talking about 2 strategies of the design, that reduction and design for disassembly, and giving a case study of the design for those strategies. Talking about, what is the circular design in a conventional design thinking, it's an open-ended design loop. It means that we design for an object or a space, and our target is satisfy that goal. For the design for recyclability is a semi-closed design loop that you think about that after making and after use, how we do deal with the waste and recycling that. But for the design for circularity, it means that how you can be more responsible in the process of creation, not thinking only about the first usage of that, but keeping them in use out of waste and for endless cycling them. It's more about how we can think about more resilient future, and not just thinking about one function, but thinking about that how the piece or that object or space could stay in the use after the first function is done. And I feel that how much design could change the way that we are dealing with this problem of recycling and waste. In 80% of the environmental impact of a product determined at the design stage. So it shows that how much the design phase is important, and the mind of creating them is important. And but from the other hand, it's important to revisit how we design, since we cannot solve our problem with the same level of thinking that create them. And I think that's a really nice quote, that we think that, okay, we cannot, if we don't revisit how we design, we cannot solve the problem that, comes out of the design process. And today I want to talk about that, how in the design practice, our team and my research team thinks about this circularity in the design. These are, 8 strategies that could be, we have been using them, and I think that are nicely, are nice strategy to think about them in the design phase. One is the avoidance, how we can eliminate the waste. The reduction, how we can minimize the resource consumption. Lightweighting, how we can have a high strength to the weight ratio and thinking about the lighter structure. And optimization of the logistic is the other one. Integration, how we can combine the multiple function so we can have more adaptable usage of the space. Disassembly and reassembly is the other one, that how we can extend the life cycle of the components. Adaptability, how we can have how we can make the structure more adaptable so we can have more than one usage or one location for the use of the project. Durability is how we can build to last. And modularity is the other one, that how we can break the large system to the smaller components so it can be reused or replaced. And the last one is leveraging digitization and how we can advancing the quality and shortening the production time by the digitization. And today I want to talk about the two strategies, the reduction and disassembly and reassembly. When we talk about, reduction, it's not just about the material, it's all about the whole process, how we can make the fabrication process, toolings, and, the logistic smaller, how we can make the components, number of the components smaller, in transportation, storage, and assembly, we can have these strategies. And the benefit of that, the strategy is in the design that having less bonding connection between the components, and we can have two strategies of having interlocking, that the pieces could be detached easily after, for any reason that we have, and or having mechanical connectors instead of wet connectors, that the piece become one piece and recycling become really hard. The benefit is all the three stages of pre-use and use and post-use. To give the example, for example, during the usage, if a component break or needs or defected, we can easily replace or repair them. And in the process of reuse, when the function of one item or space become done in one location, we can relocate them because the space could be disassembled easily. And by increasing, by adding this character to the design, we can disassemble and it expand the life cycle of a building or product. And for, reducing the fabrication waste to minimum, we can, that's going to be another strategy, that how we can use tools, material, and the mind of people to have this strategy in our design. So this is going to be the two projects that I'm going to talk more in detail after the introduction. In the reducing the fabrication waste to minimum, we have this three strategy. One is thinking about new material, how we can have the materials that have the better performance. And I think that's one of the aspects that is a little hard for designer or architects to think about them, because that's the word of mainly material scientists. The other aspect that we can think about them is thinking about the geometry, and through computational algorithm, we can have a better performance getting from the existing material. But there is a middle ground between material and geometry. And I think that's the really interesting area that digital world made it possible. How through, design process, through the digital fabrication phase, we can change the behavior of the material. So it's a collaboration between geometry and material and digital world, that you can change the behavior of the material in that phase. Giving you a little background about the digital fabrication and the constraint and the potentials, gonna be a good introduction to the topic. In the world of digital, for years we have access to the really high-end software, and during that, it made it possible for us to think about really complex form, not only as a formal expression, but in the world of simulation and getting the best performance out of shape or forms that we want to get. So in the world of digital thinking, we don't have any limitation. But when we get to the world of material, and mainly material for the construction, we are dealing with 2D materials. And dealing with the 2D materials and transforming them to the 3D, I think that's a really big challenge for moving from digital world to the physical world. And in this transition, the tools that we are dealing in the scale of construction are mainly 2D or 2.5D. When we call it 2.5D, although we have the Z-axis, possibility of working on the material, but the Z has much limitation than X and Y axis. So we cannot make really 3D form out of those tools. So that brings us to this challenge that, okay, we can draw or imagine or simulate really complex forms and very performative forms in the world of 3D, but how we can bring them to the digital, in the physical world. So it in a more, in a existing platform of the work, we produce a lot of waste. For example, bringing that surface out of the block of material, it means that we have to remove a lot of material and it produces a lot of waste. And these are some examples of exciting complex forms and architecture that mainly we produce them twice, one for the formwork, and then we cast the concrete or plywood or the actual material on the surface, and we throw the formwork out because it's one-time usage. So we almost make twice building. One of them go to waste, the other one is the actual one that we do. But the question is how, through that digital advancement, we can have get to the complex form with the minimum or no waste. So these are the two case studies that I want to share with you. That was a design process thinking about this question in our mind, that dealing with 2D material, getting to the 3D forms with no waste or minimum waste. The first design is about kerfing. Kerfing is, or relief cut, is a technique that exists in woodworking and furniture industry. For bending a wood for long time, they cut the material and make it flexible and bendable in one direction. So the technique existed before, but the thing that we did, we tried to generalize the technique and write an algorithm that how we can use the cut in the material and give the flexibility to the material that is a rigid material. So it's more about that how we can not only make a material flexible, but make the material flexible by demand. It means that how we can control flexibility and rigidity based on the function that we want. This gives us, the potential of getting, any type of surface having, single curved surfaces, doubly curved surfaces, or free form that is, give all the freedom of getting the form out of one materials. The excitement of this was, the algorithm work with the image. So it's, for example, if you have the structural finite element of the structure that knows that which part of the structure needs more rigidity or flexibility, we can import the file or the image in the system, and we can make the material flexible based on that one. But beside of the form finding process, it has another advantage that it gives the material to have different function in different parts. For example, if we want to have a hinge and rigid material, we always assemble them. We don't need to do the assembly anymore, so we can have rigidity and flexibility, or the hinge and the rigid material out of one piece. And the other part is, if you want to do the recycling, it's going to be one material that you're dealing with rather than having a, a complex assembly of the materials next to each other. After we did that we got to the algorithm and knowing that it has the capacity, we explored this in this 4 section of complex freeform, energy absorption, and architectural acoustic and reusable formwork. And we wrote we got our NSF funding for this project with 2 goals in our mind. That one was how we can mold the flat plate of material to the complex freeform for the facade of the building. And the second one was, how this microstructural geometry, we can manipulate, the range of the wave and vibration, and how we can absorb the energy. If I want to, explain it more, is the facade of building is the one that get a lot of forces from the wind, earthquake, or any type of forces that comes to the facade. And in a conventional way is you make the facade stronger, make the the framework of the facade much stronger to absorb all this energy. But our idea was how through the material we can vibrate and dissipate energy locally, so the whole building could become lighter. And the other usage of the system was about reusable formwork. So instead of having one formwork for one geometry, we can change the formwork and get different geometry out of the process. And beside of those goals, we are exploring the application of this method for designing the adaptable acoustic panel, for having the interior that could adapt itself with different function of the interior. After doing this project last year during the pandemic, we're lucky to got this project from Autodesk Gallery in San Francisco that they asked us to design a wall system, acoustic wall system for them. And it was a challenging time because we had only access to one tool. It was laser cutter. We wanted to do out of one materials. So the design was all the limitation of material performance and accessing to really limited tools that we have. The way that we designed it was using the curve method, but we designed it look like a building blocks that generated all these modules, and it comes out of a thin plywood, 1/8 plywood. Because of the different density of the cut, we could get different depths of the material. So, and I'll share with you the acoustic result that we got. But so we tested the room in a vacant position, and after the installation of the system, and the curve structure increased the reverberation time, and it become the echo of the space become much less after the installation. And it has 2 aspects. The performance comes from removing the material in a surface of the material, it become more perforated, and in the overall the geometry of the curve can work for the acoustic. And in this video you can see that how the panelization happened. We had the limits of the tools, and the other one how we wanted to assemble next to each other. And after that, after knowing the panels, we had to go from 2D to 3D, and how we can stretch the material, how much is the capacity of the non-stretchable material look like plywood to be stretched and hold in that position. And then the process of making the boxes that holds the surface of the curve. Then we assemble them in a panels that could ship to the site and assemble together. So all of those constraints, inform the design process. But I think the advantage of the system was having only one type of material. So everything comes from one typology of material. If anything happens to the structure, we can disassemble and replace them. The performance of the acoustic of the room become much better after the installation of this one. So it was a really nice, after doing the research and getting a very practical project, was a really nice, combination. So I'm really happy that this project came along at the end of our research. But the curve has more opportunity, not only in the scale of architecture, we can use it in other industries as well. Before moving to the next one, I want to share that, we had another NSF project that we used the curving and combination of that one with the smart materials, look like shape memory polymer, and the way that it works, that we can activate the materials through heats or environmental stimuli. So the hope is how we can have the facade system that could, for example, shape itself when it gets hot or cold, so it can react to the environment without the user get involved with that. The second project that I want to talk about is a nesting fabrication. And I want to switch to a method of construction or fabrication of 3D printing and larger 3D print. In a lot of companies and researchers are thinking about that, how we can have a larger 3D printers to make a larger buildings, or the whole building comes out of the process of 3D printing. But how large we can go, tools going to have a limitation. So how we can use the smaller tools to make a larger objects, that's the topic of this research. And our goal was how we can construct the complex form with the less waste material, and reducing production time and transportation and storage as well. So we generated 3 design strategies, 2D nesting, 2.5D nesting, and 3D nesting, that I'm going to explain about that one. But the whole idea is how, if we break the overall geometry, a larger geometry, how we can break it to the component that they can nest inside each other with no waste. So we can fabricate them from one piece of material and all the components comes out of that. And in a 2D, again, is the same methods. 3D is more complex, and we have we can make any free forms structure in a stackable materials, and I'll go to more detail about that. So in a 2D nesting, as I explained, is how each piece is coming. So I'll go to this slide to explain it easier. That every piece. The back of every piece is the front of the next piece. So in this case, with one cut, you can get, 2 pieces of components come out. But the concept of nesting is not a new thing. So in fabrication, we have 2D nesting, but mainly it's more about make the components as compact as possible, so we have less waste material in between. But our system is more about no waste, so how we can nest the pieces together, but it's starting the design process, how you design your surface in a way that has no waste. But it's more about designing the back of the face. You can deal with any type of surface and you apply this method for getting no waste construction. And you can break larger, geometry to pieces that could fit in your tools and with the material that you have. But all of this, we have seen this forms before, but I think that the ways of fabrication is a new way that has no waste, and can be applied in the facade of the building, or dynamic shadings that comes again with no waste construction. In a 2.5D nesting is more about dealing with the geometries that has a volume. The 2D mainly would deal with the surfaces. This is how we can break again the overall geometry in a way that the components could nest inside each other, look like the Russian dolls that, I think that that's a good representation of the idea. But the way that we do it is the second component, the outer shell of the second component is the inner shell of the first component. So they can fit inside each other. And when you produce one surface, it's producing two surfaces of two components. So we are dealing with two types of geometry. If we have a closed geometry or open geometry. In a closed geometry, the boundary of the geometry is closed, so it has more limitation that how you nest that piece inside your the components go inside each other. And the way that it works is the outer shell gonna design the inner shell. The thickening process is the thing that is matter. But because of having the enough thickness, mainly we are dealing with the geometry that have enough tilt, that we can have enough thickness for them, the components to be embedded inside. But we can combine this, strategy, and we can have more complex surfaces. It can, when we got to the logic of the design process, we can apply it to more, advanced surfaces. Again, another, constraint that we have, if we change the curvature of the design, going from positive curvature to negative curvature, we have to break down the geometry from that there. So for example, it's feasible, but we have to do it through separated stack of material. And we had an advanced studio course at CCA about, the topic was about the nesting, and one of the projects that my students were working on was using this system to design city trees for this location in city, look like San Francisco, that the location that we cannot add trees to the city. So how we can, having this biome or structure that we can plant the fast-growing, plants on the surface and add the green to the cities. But the process of fabrication are very, easy to fabricate with no waste, and can assemble and disassemble fast in the location. But when we go to the open geometry, we have more freedom. We almost can generate any typology of surfaces, and it has, brings, I think, a freedom to the design, but from the other hand, make the, the process of fabrication with no waste. When we break, the geometry, for example, if you're dealing with this dome structure, we have to cut it to the four sides, then it become an open geometry. And then we have this privilege of, designing the components or the bricks of the design. The way that we did, we have different ways of making this stack. For example, I want to make this geometry. There are lots of different ways to make this stack. So it's more look like, knowing the methods based on your construction method, you can design different modules for making a dome. And these are some of the example of fabrication. Moving to the 3D nesting, it gives you more freedom of dealing with any typology of the surface. And in this typology, I want to share with you that if we have a stack of material, it's matter that how we cut them, we can generate any typology of the structure. We can go straight, we can bend them, we can twist them, we can bend and twist them, we can tilt them. It's all about how in this space we are cutting them through different plane. And again, it's one stack of material, but it can do all the typology of the structure. It's more look like understanding the language of a design, and then we can go back and instead of starting from component, we can think about the overall geometry, and now we know that how we break it to the components. And it's exciting that, you know, it started from very simple, you know, methodology of the design, but it get to a more complex forms. And, you know, for example, this is a bridge design that, or, you know, a vault design that the components all comes from a compact structure. But just giving you, you know, how this is possible is more about the freedom of cutting in the space and not cutting them parallel. A non-parallel plane gives all this freedom of, you know, generating different geometries. And as you can see that, you know, for example, for rising a structure like at the bottom, everything comes from one stack of material. And the process of shipping, storage, assembly, everything become much simpler. It's not just the waste in the fabrication, is a lot of, you know, reduction in other parts as well. And I want to talk about the fabrication process as well, that we have two methods of, you know, fabrication. We can do the subtractive and dealing with, for example, wire cutters or any type of, you know, linear cutters, or the additive strategies. In the subtractive, you know, these are the tools that we can use that all deal with a chain or the single straight line cutters, whether the diamond wire cutter or chainsaw, we can use them. And we deal with the block of material. And with this, you know, linear cutters, we can, you know, make the component and assemble them in a 3D dimension. And in the, you know, I want to emphasize that why it's matter that we know the tools during the design process, because there are so many surfaces that need, you know, if we don't consider that, we have to do the milling, and it has a lot of waste in the construction or the, you know, fabrication phase. So this is a case study. This is the a 2-vault structure that we did in Autodesk Technology Center in Boston in 2018. At that time, I was part of Texas A&M team that we designed. It was the first, you know, prototype to test out the method is working, and we were dealing with, you know, block of the styrofoam, and we used the hot wire to cut it, and it's 2 stacks of material, and we could erect the structure without having any, you know, ladder or scaffolding, and it started from the middle of the structure. So it shows that, you know, the tools that cutting all the blocks from one piece of materials, and all the pieces can go back together and become one, you know, block again. And we use the same tools for cutting the 2 ends and make the connectors for assembly the structure. And it was without any mortar or, you know, chemical bonding, so the structure could, you know, connect them without that. And we use the, you know, the way that the Japanese joinery works, that the direction of assembly of the joints are from the direction that there is no force in the structure or gravity. So it never come off from each other. You need to know deliberately apply the force in that direction to disassemble the structure. And we use, you know, it was really nice case that after being in Boston for 40 days making the structure, we could put them back together. FedEx came, 2 package, ship it to Texas A&M, and we assemble it there again. So it has, you know, more life cycle than being in one location. So in additive strategy, mainly what you have seen in the market, or what's happening now, is extrusion of the wall. So it's really hard to make a vault or covering the space. because of the scaffold or anything that is needed. So everything is coming out of a 2D, extrusion of the system. So we are proposing these two methods of construction, print in print and print on print, based on the nesting. So this is one of the project that we did with Mehdi Farahbakhsh at Texas A&M, that we designed the nesting, and instead of printing the actual piece, we printed just the shell out of the clay, and we cast the concrete inside, and we washed out the clay, and the pieces come up out of each other. So in this method, the formwork dissolve, and you could reuse it or you can break it. But the beauty of this is, with the smaller tools that you can see here, you can produce really larger building out of smaller tools. And again, you have all the variation. We just made that as a case study. But in the other strategy is print on print. Is, for example, if you want to make this complex to curved surface, it's going to be really hard to print that, because you need a lot of scaffolding, and with the real material look like concrete, you cannot have the scaffold under the print. So we break it in a way that you can generate the modules stack on top of each other. So each module that you produce is going to be the base for the next module. So each module is a scaffold for the next module. And then you have all the blocks, you can assemble it in the final form that you want. So for example, instead of making that vault, printing the vault, you print the stackable modules. The modules goes after to make the vault. So, so the process of 3D nesting is how you can break the complex components to a way that you can fabricate them without no waste, and then shifting them to the final form that you want. But it's a nice design and fabrication process that you can make a larger objects out of the smaller tools. And with combining the 2D nesting and 3D nesting, you can make the whole structure with no waste. You can have the formwork with no waste structure, and then have the actual, for example, components that comes on the top of that, again from the same process. And as you can see that, the materials could ship to the site in a really compact container, and each piece has its own, location. And the last project that I want to share is this pedestrian, bridge project that I'm hoping that it goes further, and it's under development now, that we are working with, for the real site. And during my, sabbatical, we're pushing this project further. We have a potential project for this one. The idea is how in a remote location, or in a location that we don't have, access to the advanced technology, we cannot take the robot or things on the site, how we can ship the components of the project in a compact position and assemble it on the site. So this slide show that how this is going to work. All the pieces going to be detached from each other, and then with the process of post-tension, we can erect the structure and assemble it on the site. And the same system could be applied on the beam structure and other, structural elements as well. And in conclusion, I want to, talk about that the way that we rethink about a problem can address a lot of aspects. For example, when we started with the nesting, for us, it was, exploration of the geometry and making less waste in material for production. But it become broader than that one. It become less machining time, because you cut half surfaces. In one cut, you get almost two sides of the two piece. For the transportation, it's going to be much compact, and the storage is the same. So in overall, it has a lot of less waste and a lot of, reduction in the whole process of construction. And that was it for the presentation of today, and I'm open to the discussion, and thank you for, listening and giving me the, this opportunity to share what we have done. So I'm gonna stop sharing so I can see your face. Okay.
Thank you. That was fascinating.
Thank you, Sarah.
Lot to process.
Okay, thanks.
Thank you so much, Negar. It was amazing.
You're welcome.
So I want to ask you a question. When it comes to your design process, do you normally start from the context or the site, or how do you start this whole process?
I think, Mohammed, it has two aspects. One process that I think that we designers are not really good at it is generalizing a method. For example, we see something is working well, we don't generalize it. The thing that engineer people always do, they want to, save, a lot of, extra works for the next project, so they see what is common and could be replicated. So I think that in the process of generalization, I'm really open to the whole process of the design. For example, understanding the care thing, we didn't have that much location or site to work with. So it was more about, developing a method. But then in the process of, I think, a real project that you want to apply the method, you have to start from the site. But I think it's not just the site. Knowing that how you fabricate it, knowing that the limits of the material, knowing the limits of, I don't know, the elevator entrance, all of those things matter. Because I think it's going to save a lot of energy and a lot of, waste of things if you consider them during the design process. And I feel that in the school or in a lot of, traditional ways of thinking, we think that the design finish, then the process of construction start. But I feel that a lot of constraint of the construction should come to the process of the design. So any line that you draw has all of those information embedded inside that. But it's looked like a loop, I think, for the project, definitely we usually start from the site, but really early on, talking to structural engineering, talking to the people that they're gonna fabricate it, or even if you wanna fabricate it, limited the the tools, and then start the design from that one. But it was, for me, I work with engineering department and engineering a lot, and I learned from them that how much our profession are wasteful. It's not just material, it's about the process as well. So we don't, we don't capture what we learn or what we learn from one project and take it to the next one. We always start from scratch. And that's really wasteful. And I see it in a practice of architecture. And I'm hoping that, this, method of thinking, hopefully make the design more affordable and more accessible, because it can be more, I think, affordable if we can minimize the waste of the process. I'm hoping that I address your question.
Absolutely. This is very interesting, because I mean, the way that we normally teach architectural design is very linear, right? So one process after the other one.
Exactly.
While you are trying to kind of highlight the nuanced aspects of design that may overlap. And I think that this is very interesting. One thing that I really found quite fascinating about your presentation, even though I was kind of slightly familiar with your work, but you changed my understanding of that digital fabrication, is that Normally we look at it as a fancy technology.
Yeah.
But for example, the last project that you showed, the bridge, I mean, it could be simply a cheap, affordable bridge that could be done in any kind of village. I mean, where they cannot afford, having a concrete bridge
Exactly.
or something like this.
Yes, and from the other aspect, we think that these are luxury and these are, I don't know, but the tools, for tools, it doesn't matter what they do. They can produce a cube or they can produce a complex form. For them, the time is the same. It doesn't, for them, the complexity is not that much complex. So I think that it's more about us as a designer to rethink that, okay, now we have access to more advanced tools. We can redesign, we can rethink about what we produce. And I think that a lot of shapes of our building, what we are living in or what we are experiencing are the limitation of the tools that we had. But now that we have a new tools, we bring those perceptions with us. We think that, okay, this is the best. But from the other hand, there are people that thinking about that, more learning from nature, having more biodesign, thinking about how we can have, lighter structure, less material, and all of those. And it's more possible now because we have more tools of making those. Mm-hmm. But, I feel that we are living in an era that is really exciting, that a lot of things coming together. It's not just software, it's not just, science of material. I think advancement in the digital technology in a fabrication is a big move that I think that is going to shake up, a lot of foundation of how we make. And I think the next step going to be how we design for these tools.
Negar, I have a question. I'm a landscape architect, and so I was really taken by your city tree project. And a quick question, simply, like, what was the material that you used for that project?
Our goal was, we use the clay and clay printing, because clay is a really nice material that we use for centuries as the main material of the construction. And it's really good for even multi-story building, but it become somehow we shift to the cement and concrete and we become so detached from this material. So our goal was, printing with the clay materials, and that's going to be the nest for plantation. Okay.
I love that. I love the interplay of the shadows and the planting with the structure. And I've never really been to a World's Fair, and I'm fascinated by World's Fairs and World Expositions. And this just got me thinking about, like, the exciting possibilities, I guess, of building and material and 3D structures. And and I think, I don't know, I mean, I'm sure you've given this thought, but it just seems like a perfect application for this modularity and new thinking of structure and surface would be for, like, migrant housing or transient, where you can make something that doesn't really need a lot of mechanical works, but it could be something that goes up really fast and goes down really fast. And maybe it's for, like, disaster relief or I don't know if you've given thought to, like, what the more functional application would be.
Share with you, one of my main stream of, research about the adaptable structure, the structure that can easily be transported, not assemble or open, be used and collapse and reuse again. So yes, definitely, these are the, shelter or fast assembly, construction. These are really good methods for that one. And I'm hoping that, sharing this brings up, ideas, next generation of designer, that they think like this and it become more possible and become more available.
Yeah, it's exciting. I mean, we have this fabulous fabrication lab that I honestly have never really stepped foot in except for, like, 3 times. And so to think that, like, these are things that our students can actually start working on is really quite inspiring.
Yes.
So thank you.
Sure.
I have a question.
Hi, Carlos.
Sorry,
Yeah.
let me show up. I want I want to understand better your perspective about how your process is being. So how the different projects that you showed that I imagine are connected and you have said are connected are actually one informing the next one. And then how do you see these projecting on time? Because if I were to somehow say anything about what you're doing and connect it to the bigger issue of fabrication, probably since industrialization, I see that industrialization was a step into trying to make, it was not easy, but it was an attempt to make, to involve people with less training into producing goods that before that were not available to others. So in a way, it was some sort of democratization of both.
Exactly.
Production of goods and also the involvement of people in producing these goods.
Yeah.
But what you're describing doesn't go in that direction, which is good because we have already explored that. So could you say a little more about that direction in which you're going? That involves our students, of course.
Yeah, because you mentioned about one about the continuation of the project and how, and the other part was about manpower, skilled worker. And, I want to talk about the second one first and I go to the next. In construction, women are 4% in the whole world of construction. We are in the military is more than 10%. So I'm saying that, having this advanced technology and having digital fabrication, it make it open to more wider range of people to work in a construction field. I can mix cement if the robot is mixing. I don't mind, be on a site working with construction if the tools is responding with the level of my mind. And I think that that's really a good thing that is happening, that we have a higher educated labor in industry that can be, go back to the construction and really do the job. And instead of, avoiding them. The other part is there are lots of, techniques that are vanishing because it was labor intensive. For example, I talked about Japanese joinery, or a lot of masonry structure that had 1,000 years of history that we are almost losing the techniques because it was really labor intensive and we couldn't do that. And now the machine can do that. So I'm really thinking about that, how the clay could, or the brick system can come back to the construction because we can deal with the complexity much easier and without the cost of the labor. About the process and the continuation of the project, it's easy for me now after 4 years to look and see that how they are connected, but I never give up when a good project comes to my mind. I seek the opportunity, I try to develop them, and I think that's something that I always suggest to the student, that keep 10%, 20% of your effort for, the future development, and do not just see the scope of one project, try to take something for the next and, have the seed for the next one. So for example, the curve started with very simple. I'm saying that, it was more, discussion between me and one faculty next door. Every lunch we talk about that, okay, how we can design a new patterns that have the flexibility. And we got to the point that after and applying in the studio, students, produce a lot of, research. And I do a lot of research with undergrad. And I feel that research should happen in that level, that they know that design is a process of thinking. It's not just for PhD or master student to think. So working with them, generating all of those, and then presenting them for other, engineering school, that they saw that, okay, there is a value in this. It's not just the form, it has performance, and it become very collaborative. And now we are moving to more 3D curve that, I have some, So it become more complex on thinking about not just 2D surfaces, how we can think about this one for armors or protective surfaces. So somehow, I don't know where it's gonna end, but I try to, do this continuation of thinking, and in different projects, somehow, explore some aspects of that. And the other thing that I'm hoping that it happens is more merging, innovation in academia and innovation in practice, because I feel that we are so much detached in, thinking about that, what they need and how we can, I don't know, a lot of good ideas generate in research labs, but it doesn't go to the actual, projects. So that's my next goal for, this period, that how we can really apply these findings in a practical team. I hope I address some of your questions.
Some.
Yeah. Okay, we can continue. Yeah. But you're at Texas A&M.
I was a student at Texas A&M. Yeah. But
Yeah, because you're. Yeah, I see that.
That's what I was. That's what I was hiding because I didn't realize that I was dressed as a.
No, I taught there for 4 years, so I saw that. I've become happy that you
yeah, I left A&M in 2009, so it's been
okay.
some time.
So yeah, I joined 2014, so we didn't overlap, but yes.
Okay.
Okay, thanks a lot.
Oh, thank you so much. This was fantastic. I really, I'm just excited and kind of, as I said, inspired by your work. And we will definitely have our students watch the YouTube video.
And you have my email address. The student has my email address. I would be happy if something comes up, question or anything. I will be happy to answer that.
Okay, wonderful. Thank you so
much again, Negar. It was really inspiring. So I will. Yeah, I mean, you changed my perception of this technology. So yeah, we'll be sharing it with our students.
Okay, thanks.
Yeah.
Thanks for having
me. Thank you so much again.
Okay.
And thank you, Sarah, for everything.
Oh, thank you, Mohammed.
Yes,
That's exciting. Thank you so much. We'll see you all soon.
Okay, bye-bye.